So we looked at the initial value problem, and now we'll take a very brief look at the boundary value problem, okay? So what is the boundary value problem? Well, we focus on n equals 2. We focus on second order linear differential equations. So for a linear differential equation on interval I, the 2-point boundary value problem, or just boundary value problem, is to solve this differential equation, so this non-homogeneous linear differential equation, subject to the boundary conditions that we see here, where a and b are in I, okay? So typically these a and b would be the endpoints of a closed and bounded interval, okay? But we could have more general boundary conditions. So here we specified, so notice how this differs from the initial conditions. Initial conditions, you would specify the function y at some point x naught, okay? And then you'd specify its derivative at the same point, and you know, that it would be equal to y1. So you would have here b and a are in general, you know, are not the same. So the a and b are distinct, okay? So think about it this way. An initial condition, say for acceleration, a problem dealing with acceleration, which is a second order problem, right? Acceleration is the second derivative of position. So we would have our equation of motion, which is mass times acceleration equals the force, m d squared x dt squared is equal to the force. And we would specify then the initial position, so x at t naught, and we would specify the first derivative, x prime at t naught. What is the first derivative? The velocity. So that's the initial value problem. Here it would be different. It would be, instead of specifying, you know, you would give the initial position, but you'd also give a position for a future time instead, okay? So you would say, okay, at the initial time, you know, say a ball that was about to be thrown is here, and at some future time it's there. So that's called a boundary value problem, to make the distinction. Whereas the initial value problem, you specify at the initial time both the position and speed. Okay? There's nothing special about position. We could have also just said, well, we're going to specify the speed at the initial time and the speed at the future time. So instead of having a ya equals y naught and yb equals y1, you would have a y prime a equals y naught and y prime b equals y1. Okay? Or you could specify the position at some initial point and then specify the velocity at some future point. Okay? Or specify the velocity at some initial point and specify the position at a future point. So all of those are boundary value problems, and more generally, you could have a mix of derivatives and in the function to specify your boundary condition. So more generally, it'll look like this, okay, where alpha 1, alpha 2, where all of these are constants. Okay, so if you set these to the betas to 0, then you're in this territory. You could set the alphas to 0, and then you would be specifying, say, the velocity, okay, at two different points. Or you could have some general mix that just, you know, at some initial time you specify the position and the velocity, or in some linear combination of them, and so on. Okay, so that's the most general kind of boundary conditions. And of course, the BVP may be generalized to higher order differential equations. Okay. Let's look at an example of a boundary value problem and just see, you know, get a glimpse of the type of solutions that we would be getting. Okay. All right, so we have this differential equation here, x prime plus 16x equals x double prime plus 16x equals 0. And it has the general solution that you see here. You definitely see this often with the spring mass system, okay? That differential equation. And now we'll want to impose some boundary conditions. If we impose the boundary condition x of 0, so we get a general solution to this differential equation that looks like this. Now we start imposing boundary conditions. And we're going to see what kind of boundary conditions, what kind of solutions we get depending on the boundary conditions. So we have, if we impose x of 0 equals 0, x pi of 2 over 2 equals 0, let's impose the condition. So x0, this is coming on the right hand side. We're getting this from applying, so plugging in x equals 0 into this equation. And on the left here we're getting this from the boundary condition. So if you plug it in and you do the math, you basically find that C1 must be equal to 0. Now impose the second condition, x pi over 2 equals 0. So you just plug in pi over 2. 4 times pi over 2 is 2 pi. Cosine of 2 pi is 1. But sine of 2 pi is 0. And so this second boundary condition is satisfied again when C1 equals 0. So we didn't say anything about C2. We could respect both boundary conditions by just having C1 equal to 0. And so we get many solutions. So we'll take this general solution, just put C1 equals 0. And now you have solutions that will respect these boundary conditions. So we have infinitely many of them for those boundary conditions. We found an infinite amount of solutions that satisfy the boundary conditions for part A. All right, let's look at B. B has x of 0 equals 0, but x pi over 8 equals 0. So again, we impose that first condition, it gives us C1 equals 0. We impose the second condition, it gives us C2 equals 0. So x of t equals 0 is the only solution there. Okay, so we both conditions imply, the first condition implies C1 0, the second C2 equals 0, and so what are you left when you plug in these C's here? 0, 0, right? So you just get the trivial solution, and that's the only solution. Okay? So for these different boundary conditions, we got a unique solution. What about C? Well, here we have x of 0 equals 0. Again, that's going to give us C1 equals 0. But x pi over 2 equals 1. And when we try to impose that, notice what that's telling us, okay? So cosine of 4 pi over 2, that's cosine of 2 pi. And so that's 1, okay? And sine of 2 pi is 0. So this is telling us that C1 needs to equal 1. But wait a second, C1 equals 0. So those conditions are incompatible. They're inconsistent. So that means we get no solution, okay? There are no solutions because it's impossible to satisfy both those boundary conditions. So we just looked at one differential equation, and we saw how varying the boundary conditions, we could get infinitely many solutions, we could get a unique solution, or we could get no solution, okay? So we don't have that same guarantee that we had when dealing with the IVP, the initial value problem. There, we found that as long as AN does not equal 0, the A's are continuous, then we're guaranteed a unique solution to the IVP, okay, where you specify the first n-1 derivatives and the function at the initial point. And why is that? I mean, you could go back and take a look at the proof. What would happen here is we would try to impose each of these boundary conditions the same way we imposed each of the initial conditions. Okay, but we don't have that same, there we relied on the Wronskian not being equal to 0. Okay, because we specified the first n-1 derivatives for the initial value problem, we were able to use the fact that the Wronskian was non-zero and that we had this fundamental set for the associated non-homogeneous equation and prove that a unique solution exists. We could uniquely find all the C's. Here, we'll still get the general solution, but we can't necessarily say that we're going to find some solution to the C's. Okay, and that's because we don't, this fact, the Wronskian being non-zero, yeah, that's still true for any fundamental set, but for boundary value problems, unless we're specifying those first n-1, we just won't use this fact, okay, to get a unique solution to the C's. All right, and as you could see, we even run into problems where we get inconsistent solutions to C. So it's not just that we get infinitely many or, one, it's also that we could just find none and that they contradict each other. Okay, so if you go back in that proof, you see that that's, in that proof we relied on this fact, it helped us, whereas this fact will not help us if we try to prove a similar theorem of the existence for the boundary value problem, at least as we have formulated it here.